Hello, I'm Huntley. I'd like to introduce a neural reconstruction method called the neuron field made explicit geometric representation, which simultaneously reconstructs the scene geometry, material properties, and lighting information from RGB images. Neural radiance fields, or NERV, as we commonly refer to it, is a cutting-edge method for the reconstruction and rendering 3D scenes. It leverages deep learning to create a continuous and intricately detailed three-dimensional model of the scene, based on a collection of the image captured from various viewpoints. The function of NERV is using a deep neural network to model the volumetric density and the color of the scene. However, in NERV, the properties of the scene are not separate from the effect of incident light. As a result, novel view can only be synthetic under the fixed lighting condition present in the input images. Unlike NERV, explicit mesh-based representation facilitates highly efficient rendering. The mesh topology will accurately estimate both primary and secondary light rays through the ray mesh intersection queries. However, traditional inverse rendering technique rely on the explicit mesh representation, either require a predetermined mesh topology or reduce the surface mesh through a sign distance function on a volumetric grid, thus being limited by the grid's resolution. To date, this technique can only predominantly achieve the high-quality outcome for the smaller and object-focused scene. The key idea of the method is the novel hybrid rendering pipeline that merge the neural volume matrix rendering from primary rays with traditional real-time mesh ray tracing or the secondary rays. Rather than modeling the radiance directly, our approach breaks down the scenes into several layers based on the physical properties of the materials. It uses a collection of the input image to reconstruct the scenes based on the albedo, material geometry, and the high dynamic range lighting. More specifically, we represent the intricate property of the scene using a neural field and estimate the primary rays, as we call G buffer, with a volumetric rendering. To model the secondary rays that produce the higher order lighting effect, we convert the neural field into an explicit representation and perform the physical-based rendering. The underlying neural field enables us to represent the high-resolution details, while ray tracing secondary rays using the explicit mesh reduce the computational complexity. The proposed hybrid rendering is fully differentiable and can be embedded into an optimization scheme that allows us to estimate 3D spatial varying material properties, geometry, and HDR lighting of the scene from a set of post-camera images. Assets reconstructed with our method are compatible with modern graphic pipeline and can be exported into popular 3D formats like GLTF and the UASD for use in a graphic engine, including NVIDIA Omniverse. Our strategy can be summarized at 3 points. 1. We propose the normal views representations that encompass the scene into the geometry, spatial environments, materials, and HDR lighting. 2. To achieve efficient ray tracing with the neural scene representation, we introduce a hybrid renderer that renders the primary rays through the volumetric rendering and model the secondary ray using physical-based rendering. This enables high-quality inverse rendering of the large urban scenes. 3. We model the HDR lighting and the material properties of the scene, making our representation well suited for the downstream application, such as the relighting and the virtual object insert with cast shadows. Here are some implementations. Our technique can reconstruct the complex scene from autonomous driving data. These reconstructed sequence can undergo relighting under the various conditions, provide a rich source of training and testing material for the perception algorithm. Additionally, this reconstructed scene can be enhanced with synthetic or AI-generated objects to which physical principles are applied. This enables the photorealistic integration of the object into the scenes, offer a scalable approach to generate synthetic data. Thanks for your watching.